Hello everyone. In the previous lecture, I discussed the gas-filled counters like ionization chambers, proportional counters, and Geiger-Müller counters. Now, these gas-filled counters, you will notice that the density of gases is low, and particularly for gamma rays, they are not very suitable. So now I will discuss the detectors which are solids in shape, solid state type of detectors. They can be emitting light or they can be semiconducting type. So first lecture I will take as the scintillation detectors. As the name itself applies, when the radiation falls on this material, certain materials are luminescent materials or they fluoresce. So they are basically the fluorescing materials, and the light falls when the radiation falls on them, they produce light, and then that light can be used in a photomultiplier tube to generate the electrons. That is the type of detectors we'll be discussing in this lecture. So scintillation detectors are those detectors which, when radiation falls on them, produce light. Now there are certain requirements for a good scintillator material. The first thing is that this should have a high scintillation efficiency. Like if you have a 1 MeV of the gamma ray, then how much of the energy of the gamma ray is utilized in producing light? So that is an important point. Higher the scintillation efficiency, higher is the detector resolution becomes higher. Then once this light is produced in the crystal, it should be taken out of the crystal, and so that the PMT can generate an electronic signal from here. So this should be transparent to the wavelength of its own emission. The second important property. Then the decay, the fluorescence decay should be fast, so that all the light is generated in a very short span of time. Otherwise, if it is a phosphor material, phosphorescence, then the light will be produced very slowly, and we may not be able to integrate the charge that is being collected. So short fluorescence decay time, typically few nanoseconds to few microseconds, the order of time for fluorescence decay. Fourthly, to make it compatible with the PM tube, we require that the refractive index of the crystal should be compatible, same order as glass, because the PMT has a window made of glass. Sometimes you have the UV radiation being emitted, so you require the UV compatible, UV transparent PMT windows. So in general, for normal PMT, the glass window is used, and so refractive index of the crystal should be of the order of 1.5. And lastly, it should be possible to manufacture these crystals in large sizes. So all of them are important requirements for a material to be used as a scintillator. So the block diagram of the detector scintillator is, you have a crystal. The crystal could be 1 inch by 1 inch, 2 inch by 2 inch. There are some crystals which are available in 3 inch by 3 inch, or even 5 inch by 5 inch. So it depends what type of application you have in mind. Then you have you optically couple the crystal with the PMT. If you have a 1 inch by 1 inch crystal and you have a 2 inch by 2 inch PM tube, you have to have some optical coupling. So there are optically coupling materials. Then you have you have the pre-amplifier. PMT will have its filter circuit. Apply the high voltage to the anode of the PMT, and then the pre-amplifier signal is amplified using a signal amplifier, and the amplifier output analog signal you can take to multi-channel analyzer, or it can go even to a timer scaler. So this is a block diagram of a scintillation detector. The heart of the detector lies in the crystal, which has these above properties. Now the scintillators can be of two types. One could be the organic scintillator, or it could be inorganic scintillators. Organic scintillators are having their own advantages and their own disadvantages. Advantage is that they have a molecular structure, so each molecule is fluorescing, unlike inorganic scintillators where the entire crystal lattice generates the light photon. So organic molecules with pi electron structure, like pure organic crystals, anthracene, stibine, and so on. So each molecule, when the light falls, when the radiation, when it gets ionized, so you can excite the molecule, and the excited molecule can lead to fluorescence. So you have this is the typical diagram for a fluorescing molecule: the singlet state, ground state, excited states. You can also have the triplet state, which will undergo phosphorescence, and the singlet excited state will undergo fluorescence. So there are several molecules which will undergo fluorescence when they are ionized or they are excited. But the typical ones which are used in detection of radiations are called the liquid organic scintillators, like TOPO. This is the tri-N-octyl phosphine oxide, or PPO, 2,5-diphenyl oxazole. Basically, you have a pi-electronic structure in molecules, conjugated double bonds that will give you the fluorescing nature of the molecule. So you have each organic molecule acting as a fluorescence. Now, these organic molecules, they have to dissolve in some solvent. So you can use toluene, xylene, and dioxin. So for organic solution, you can use toluene, xylene. For aqueous soluble, you can use dioxin. And many a times, this fluorescence of these molecules may not be compatible with the PMT, photomultiplier tube. So you use some other reagents called wavelength shifter, like Popov, 1,4-bis-2,5-phenyl oxazolyl benzene. So these molecules take the radiation from the fluorescing molecule, get excited, and redshift the light that is emitted. So you have a redshift. So then that the light that is emitted from these molecules will be compatible with the PMT. So these organic molecules are very good for detecting the alpha particles or beta particles of low energy, but they have a low photofraction because they are mostly hydrocarbon material, carbon, hydrogen, oxygen. And so the photofraction, the photoelectric effect, which requires high jet material, that is very small. So there are some applications which they are useful, but particularly for gamma counting, they are not very useful. So organic scintillators are mostly used for gross counting of alpha and beta. So alpha, liquid scintillation counting. Alpha, you have, for example, you have radium, or you have polonium or plutonium. Very small quantity, microliters of solution can dissolve in an organic solvent. So here we have a vial, this is 30 ml vial, and you have this yellow is the cocktail of like TOPO and PPO and Popov, and you dissolve the activity in this organic solvent. So you have toluene or xylene, in that you have this activity, and then now this active sample is a part of the detected material itself, and then you put it over the PMT, and the PMT will take the light signal, which you can go to the subsequent circuitry. So here the advantage is that the sample is dissolved in detected material. Every time you want to count a new sample, you take a new detected solution. So the efficiency is 100%. Because all radiations are being stopped in the detected material. For beta counting, efficiency is close to 100%, but since the range of beta is more, some part of beta may get lost. But mostly, their scintillation counters are used for alpha beta counting. There are a class of materials where you can polymerize a fluorescing material, so it's a solid material, but still low Z. They are called plastic scintillators. So these plastic scintillators are used for gamma ray spectroscopy, but for timing, not for energy spectroscopy. So organic molecules have very slow, very short fluorescence decay time of the order of picoseconds, and because of that, they find applications wherever you are doing lifetime spectroscopy. So lifetime spectroscopy, where you use, like in positron annihilation spectroscopy, you are detecting the time between the birth and decay of a positron or a positronium atom. So there you require very fast detectors which will generate a signal within hundreds of picoseconds. And for those purposes, these organic scintillator based detectors are very useful, but they do not have higher atomic number. And so for gamma counting, they are not very useful. For time purposes, yes, they can be utilized. Now I come to the workhorse of gamma counting is called the inorganic scintillators, particularly the sodium iodide doped with thallium. So inorganic scintillators are now based on their band structure. So you have any crystal, a single crystal of sodium iodide, a single crystal. So you have the valence band and the conduction band. So it is an insulating material. The band gap, the difference between the conduction band and valence band is of the order of 5 electron volt, which falls in the insulating material. Sodium iodide as such is a very poor scintillator, does not emit fluorescence with high yield. And secondly, even if it is emitting fluorescence, that is in the ultraviolet region. So sodium iodide as such is not used for counting of gamma rays. Instead, if you dope this sodium iodide with a small quantity, 0.1% of thallium, which is as an impurity, then this thallium impurity generates activator sites in between the valence band and conduction band. And now, so when the radiation is exciting this valence band electron to conduction band, these electrons can get trapped in the activator excited states, and these activator sites then undergo fluorescence to come to ground state of activator site and thereby emit light which is incompatible to the photometric tubes. So because by adding 0.1% of thallium to a sodium iodide crystal, you can have a fluorescing material of high fluorescence yield and compatible wavelength to the PMG. So the thallium impurity acts as a wavelength shifter like pop-up in the organic scintillators. Even then, the fluorescence intensity is not very high because there are competing processes to fluorescence. For example, the electron, when it is generated in the conduction, it is going to conduction band. This may occupy activator site, which all these activator sites may not undergo fluorescence emission to ground state. So the ground state, so those radiations which are like they can be radiation-less transitions, so those are not useful for detection purposes. So radiation-less transition between excited and ground state and the trapping of these electrons in the activator sites, whose transition to ground state is forbidden, they will lower the fluorescence intensity of these crystals. So sodium iodide thallium, though even if this doesn't have very high scintillation efficiency, but it is the workhorse of gamma counting. So advantages are that it is mostly used scintillator since 1950s. It is available in large sizes, 3 inch by 3 inch, even 5 inch by 5 inch size is available. You can machine it in such a way you can make a well type. So you can have a detector, So you have a well. You can put the counting tube. You can put in this. So you have a well type sodium iodide, and the tube. So the source is here. So it is almost giving you 100% geometric efficiency. So counting tubes can be inserted in the well of the sodium iodide thallium. Excellent light yield, though it is not very high, but you see 13% is the efficiency, but still in parlance of scintillation detectors, it is called excellent. Only thing is it has got, it is a hygroscopic in nature. So when you are making a detector, you have to house it in a airtight container. So hermetically seal it in a aluminum casing. And also, so you should make sure that moisture does not get inside. Resolution is not very good. It is about 6%. We'll discuss more on this. The scintillation efficiency is one of the best that you have among the different scintillators. Though it is much less than 100%, still the 13% is considered to be pretty good. Now, why this resolution is so poor? We expected about 0.1% or 0.2%, but it is 6%. And because of that, the reason is that all the photons that are produced in the crystal do not reach the photocathode of the PMT. So the light collection efficiency is very, very low. Similarly, the photocathode has its own quantum efficiency. It is much less than 100%. So first of all, the crystal itself has got very low quantum fluorescence yield. Then all the light that is produced does not reach the photocathode of the PMT, and the photocathode does not have a good quantum efficiency. So because of these three factors, this sodium iodide thallium, or for that matter, any scintillator does not have a good energy resolution. So let us do an exercise here to compute the energy resolution of a sodium iodide thallium. Why this resolution is so bad? So typically, let us see for a 1 MeV gamma ray, So out of the 1 MeV gamma ray, the scintillation efficiency is 13%. Means what? 13% of this 1 MeV is utilized in generating photons. And so you can see, so 1 MeV means 1300, 1 MeV, so 130 keV. 130 keV energy of the gamma ray is utilized in producing scintillation. And if you have 4 electron volt is the energy of each photon, then you can calculate how many photons will be produced. So you will be having 32500 photons of 4 eV. 32500 into 4 will be 1300 electron volt. So that is how 130 keV. You can calculate 13% of 1000 keV, 130 keV, and 130 keV divided by 4 eV will be 324500. Now this many photons are produced in the crystal. All of them are now going to photocathode. Only 20% of them may reach, because you have a crystal here and you have PMT only on one side. So the light can be produced in all directions. So you will have very small fraction reaching the photocathode. So that is, let us say, 20%. So out of 32,500, only 6,500 reach the photocathode, and then photocathode has its own quantum efficiency, that's say 20%. So out of 6,500, only 20%, 1,300 photoelectrons will be produced at the photocathode. So these are the primary ion pairs, like the charge carriers, which will determine the resolution of detector. Because after this, now the subsequent multiplication of electrons in the proton multiplier tube, you will get 10 power 7, 10 power 8 electrons in the anode, but they will not increase the resolution, because any multiplication will not improve the resolution. It is the primary ion pairs of electrons that will determine the resolution. So the resolution, you can see 100 into 2.35 upon root of n, that is n is 1300, so it becomes a 6.5%. So I hope this explains the reason for the poor energy resolution of scintillation detectors. Even then, you will find that the sodium iodide thalliums are widely used in counting of gamma ray radioactive samples. Resolution is poor, 6 to 7%, but the efficiency is very high. So one of the positive points of the sodium iodide thallium detector is the detection efficiency is very high. Why it is so? Because of the atomic number of iodine, that is 50. So high atomic number means the photoelectric effect is more. So because of that, the majority of the interaction will be with the photoelectric effect, though Compton scattering also will take place. But because of the high Z of the iodine, photofraction is very high. So typically, sodium iodates are in fact available also in well type. Just now I explained what is the well type sodium iodide. And if you put the sample in the well, then you get almost 100% efficiency, because geometric efficiency is not 100%. So for gamma ray energy less than 500 keV, the efficiencies are of the order of 100%. So for example, you have 100 keV, 200 keV gamma ray emitting source, the efficiency is close to 100%. So this is the typical gamma spectrum. As a function of E gamma, you have the counts, and you have this Compton edge. So you have the Compton edge, and this is called the full energy peak. This full energy peak can be due to photoelectric effect or multiple Compton scattering. So this is a broad peak because of the poor resolution, and so it is sitting on a background. So you can take the area of this peak by what you call as the linear subtraction of the Compton background. So Compton is like linear. So you can make a trapezium and subtract. So take the gross area, subtract the background, and get the total effective peak area of the gamma ray peak. And then this peak area you can divide by time to get the count rate, counts per second, and then subsequently you correct for the efficiency and the abundance to get the absolute activity disintegration per second. So while sodium iodide thallium is the workhorse for gamma counting when you don't need high resolution, but there are other scintillators like cesium iodide thallium, barium fluoride. Barium fluoride is used for it is emitting UV radiation, so you have UV compatible PMT, but it has got fast timings. The sodium iodide thallium has got a fluorescence decay time of 230 microseconds, whereas barium fluoride has got in 200 picoseconds. Zinc sulfide, silver doped. Zinc sulfide is not a single crystal; it is a polycrystalline material, and doping with silver. Silver is like that wavelength shifter. So for alpha counting, we have very thin layer of zinc sulfide powder on a perspex plate and coupled with the PMT, you can use for alpha count. Bismuth germanium oxide, BGO. Bismuth is a good material. High Z of the bismuth makes it very high efficiency, but resolution is worse than sodium iodide thallium. And recently, one new detector has come in the market, lanthanum bromide detector, which is doped with cerium. So lanthanum bromide detectors are another class of detectors which we will be discussing very shortly. So in commercially, you will find a sodium iodide thallium detector, well type. So this is you can see the pencil source. Half of it is going inside the detector well, and this is the photomultiplier cube. This is the bleeder circuit, and you have the unit timer scaler, which will be giving you the counts. It will not give you the gamma ray spectrum. If you want to get the gamma spectrum, then you can connect this with a multi-channel analyzer. So the well-type sodium iodide thallium is very widely used in the laboratories. It has got the 100% geometric efficiency, and so for gamma energy of 500 keV or low, it has got the even absolute efficiency as 100%. And the lower energies, let us say 50 keV and below, at that energy, because the aluminum casing, it has got the aluminum casing, that aluminum will reduce the gamma ray intensity for the low energy gamma rays, and so efficiency will become low for low energy. So typically you will find that the efficiency, energy of the gamma ray efficiency, so it should have been going down like this, but that at low energy again will fall down because of the aluminum window. So this is how the efficiency for detection of gamma ray will change with the energy of the gamma ray. So almost up to 500 keV, you will find efficiency is close to 100%. Now, this is the advancement which has taken place in the last 1 decade or so, more than just 10-15 years. So there are always research going on to develop new detector materials which are having better performance than the existing detector systems. And in this series, a new crystal lanthanum bromide cerium doped synthesis detector has been developed. In fact, in Technical University Delft, they have developed this crystal. This detector offers the best energy resolution among the scintillators. Not any detector, but among the scintillators, these detectors offer. So, like since the 1950s, sodium iodide thallium has been rolling for the gamma counting, for gross gamma counting, and even for pure gamma sources. But this detector was developed and it has got 30% higher yield than sodium iodide thallium. So when we say 30% higher fluorescence yield means it was having 13%. Sodium iodide thallium was having 13% fluorescence yield, lanthanum bromide has got 16%. So because of high yield, you will find the resolution is better because more photons are produced for same energy. So the light yield photons per keV, sodium iodide thallium 38 photons per keV, lanthanum bromide cerium 63 photons per keV. Compare this with barium chloride and BGO. So if the number of photons per keV are low, resolution is going to be worse. The resolving time, the fluorescence decay time, how fast the fluorescence is decaying. I was telling that this for sodium iodide thallium is to 230 nanosecond, for lanthanum bromide is 26 nanosecond, barium fluoride is 0.8 nanosecond, BGO 300 nanosecond. So it is better than sodium iodide thallium in terms of the life fluorescence decay time as well as the number of photons per keV. So the resolution you can see sodium iodide thallium 7%, lanthanum bromide 2.8%. So you can see here, this is a typical resolution of a lanthanum bromide detector, 2.8%. So this has in fact almost revolutionized the gamma ray spectrometry with scintillators. We'll discuss subsequently that this semiconductor detectors are much better in terms of resolution. But this lanthanum bromide detector, not only in terms of resolution, but efficiency wise also, both wise is better than sodium iodide. Because of that, more and more now researchers are using it. So the cost is higher. The cost of sodium iodide lanthanum bromide is much higher still because the production is not that high. And only one drawback is there, that 138 lanthanum, which is a long-lived isotope of lanthanum. Lanthanum 139 is the naturally occurring radioisotope, stable isotope, but because of this presence of 138 lanthanum, which has got very long half-life, which is available in natural radium lanthanum, and it is emitting a gamma ray, high energy gamma ray. Because of that, if you have a lanthanum bromide detector, you will have a background peak in gamma spectrum. So though that background peak will be very, very small, but if you count for a long time, you will find a peak will appear somewhere in the high energy region. So that is the only drawback. But other than that, lanthanum bromide is going to score all points with respect to sodium iodide and other scintillation detectors. So I have tried to explain the fundamental principles of scintillation detectors, both organic as well as inorganic. Organic scintillators, good for alpha beta counting in liquid solution, where you get higher 100% efficiency, but resolution is not good in terms of energy because of the hydrocarbon nature of the organic molecules. Whereas the inorganic scintillators, they are having rugged high Z materials, sodium iodide, BgO, lanthanum bromide. Because of that, they have high photofraction, and hence the resolution is also good, efficiency is also good. But now subsequent lecture will discuss the semiconductors, germanium, silicon, which though have low Z, because of that the efficiency is not very high, but you will have excellent resolutions and they are ideal for gamma ray spectroscopy. So I'll stop here. Thank you very much.